Welcome to our webcast, Design and Deployment Best Practices for a Reliable Fiber Optic Network, sponsored by Panduit. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering. To get the best results from the Control Engineering webcast platform, please make note of the following as you participate in today's event. If you're having technical problems with audio or the slide presentation, click on the question mark at the top right-hand corner of your screen to bring up a list of system checks to make before escalating to an online technician. If you're experiencing issues with your slide or audio, please refresh your browser or click the Refresh Media button directly under the presenter's headshot. You can control the volume settings of this webcast by adjusting the volume on your computer or adjusting the volume on the webcast platform. If you need a technician, type a message into the Ask a Question box and someone will get back to you as quickly as possible. Individual technical questions will be answered in the Answered Questions area on the left side of your screen. You can use the Ask a Question box on the left side of your screen to type questions for the speaker during the presentation for the Q&A session at the end. You may ask questions at any time during the presentation, and we'll get to as many as time allows. Questions that are for today's presenter will be answered verbally during the Q&A session at the end of the webcast. To download presentation slides, or if you'd like to download a certificate of completion from today's event, use the Event Resources tab on the left-hand side of your screen. This webcast is being recorded, including the Q&A session. We'll post the archive on the Control Engineering website in a few days, and we'll send you an email message with a link connecting directly to it after it's ready. Today's webcast sponsor is Panduit. Thank you for supporting this program. Now I'm happy to introduce today's distinguished speaker. Bob Elliott is the Business Development Manager with responsibility for copper and fiber cable and connectivity with the Industrial Automation Infrastructure Group at Panduit Corporation, a global leader in network and electrical infrastructure solutions based in Tinley Park, Illinois. In his position, Bob is responsible for the development of business case to approve projects and programs that lead to new business generation and new product introductions. Bob has responsibility for understanding solutions to customer problems and requirements, defining programs and new product performance, putting forward to management recommendations to expend resources to design, develop, and release new products that are in alignment with the Industrial Automation Infrastructure Group's goals and objectives. Bob's been with Panduit for 10 years with experience in engineering design, research, development, and product line management. He is a graduate of Queen Mary College, University of London, with a Bachelor of Science in Physics with Electronics and a PhD in Reflector Electromagnetics. I'm Mark T. Hosky, webcast moderator and content manager for Control Engineering since 1994. Before we continue, please take a moment to remind yourself about dealing with technical issues during this presentation. And now on to Bob's presentation.
Thank you, Mark, and thank you everyone for the opportunity to talk today about the design and deployment best practices for a reliable fiber optic network. Just a very brief overview of the agenda. Set the stage with an introduction, talk about applicable fiber cabling standards. We then talk about reference architectures and zone architecture in particular. Then we head towards selecting the correct fiber. We describe some applications and finally round off the presentation by describing some best practices. As we've seen, fiber is becoming a more and more relevant part of industrial applications. There are strong needs to provide performance in the network. At the same time, familiarity is growing and the skills need is being addressed, making the deployment and installation of fiber easier. In today's presentation, we're going to build your familiarity with fiber, including its application in the industrial space, the standards and architectures that provide application guidance and use cases. We'll also talk about the selection of fiber based on its place in the network topology and round this off with best practices, identifying different fiber types for use in different areas of the industrial application. So we want to start by talking a bit more about fiber and its use in industrial applications. Many network and controls engineers are weighing the use of fiber in more parts of the network versus something they and the installers may be more familiar with, for example, twisted pair copper cabling, I'm sorry. So some of the areas, in fact, where fiber would be used in the industrial space versus that of copper, obviously the big one here is the ability to span longer distances than a twisted pair copper cabling channel. Currently, twisted pair with supporting Ethernet is limited to distances of 100 meters, and of course in the office or in local areas this is fine, but some of these industrial applications involve huge plants occupying many hundreds of thousands of square feet. So the ability to span longer distances is very much required by fiber. Fiber also gives advantages in terms of the overall bandwidth that can be covered. That translates directly to the data rate. It also helps with situations where convergence is required. That's the recovery speed, for example, if a switch should fail. And of course, fiber gives security. It's both security from radiated signals that might arise from a cable, but also its susceptibility to electromagnetic interference, that is, outside interference. There are, in addition, industrialized armored fiber types. These are very common, that provide extreme durability and protection against mechanical sort of knocks and scrapes. And finally, the reliability and speed of installation is always improving and reducing the total cost of ownership. So I like to look at this slide as really the pivotal slide that underlies the whole of really what we're going to talk about here. That is the converged plant-wide Ethernet architecture that's been outlined by leaders such as Cisco Systems and Rockwell Automation. Really sort of shows the key elements of a successful design of an Ethernet IP network design. And really, when you look through this logical diagram, it really points to the fact we need to understand the application, then develop this logical framework. The diagram on the right is really a topology that sort of shows the network schematic and where the largest items of equipment are in terms of switching, firewall, and then as the enterprise network transitions to the industrial automation network, you can see the existence of cells or manufacturing zones in at the bottom of that diagram, level 0 to 2, and that's showing 3 different architectures that are supported by this topology. This is the familiar star topology on the left, the ring topology in the center, and a bus ring topology on the right-hand side. So translating this a little bit more to the actual shop floor environment itself, what we see here is a typical factory floor layout indicating where some of these key physical layer elements will be located. The idea at the bottom right-hand side, we see a so-called micro data center. This is effectively is an equipment room for shop floor computing equipment. Fiber would come from this, for example, to along those pathways to a zone enclosure, and from the zone enclosure, which might itself include switching equipment, would, for example, come copper links that would be connected to each of a number of control panels. So having sort of set the stage, we now want to kind of take a slight change here to talk about some of the standards that are relevant and pertinent to the design of a reliable physical layer network. One of the key documents that I think here is the TIA, that's the Telecommunications Industries Association Standard for Industrial Premises. It was devised by the TR 42.9 Industrial Infrastructure Subcommittee and was first published, or was most recently updated and published in May of 2012. An addendum has just been added very recently to that standard, outlining and defining the so-called M12 X-coded connector that has 8 pins and is able to support higher data rates. And we'll talk about that a little later. So this standard kind of defines the industrial environment in terms of different areas, the industrial areas themselves, the telecommunications spaces, that is something like the telecommunications room, the pathways, talks about fire stopping, but also backbone and horizontal cabling, and grounding and bonding best practices. TIA 1005 fits within a larger framework of telecommunication standards that have been developed and released by the TIA. And what I have in this diagram is on the left-hand side, we define the common standards. These are really the baseline documents for describing some of these areas and attaching applicable standards and performance requirements to them. TIA 568C.0 then forms the basis for premise standards, that is, a particular type of application takes 568C.0 and then adds onto it its particular requirements. For example, a data center or a healthcare facility, or as we see here, the industrial premises. Then finally, you can see on the right-hand side of this diagram the component standards, C.2, which is applicable for copper cabling, and C.3, of course, which is applicable for optical fiber. I want to just talk now a little bit about zone architecture. This is the idea of, you can see here on the left-hand side, what I'm trying to depict here is where cabling is routed from a telecom room or a network room to each device. It could be a control panel, for example, that is then associated with the machine. The problem with this is that it's difficult to carry out moves, adds and changes on these this home run kind of design, so that a better practice is shown on the right-hand side, which is to use pathways carrying common data cables, perhaps then to a zone enclosure, marked in this figure with Z, and then shorter cabling runs from the zone enclosure to those different machines. It reduces installation time, for example. It's easier actually to future-proof that design as well. What is future-proofing? Future-proofing is the idea that you don't design your cabling, your physical layer, to accommodate today's network needs. You actually look for tomorrow's needs. For example, we've seen cases where copper cabling, for example, and fiber also, can be expected to last for 10, 15, or 20 years. The kind of data that it would be run in future years could exceed the performance requirements of that cable. So this does allow you to take into account future-proofing in an easier manner. For example, installing a high-performance fiber between that network room and the zone enclosure, and then copper cabling that can be upgraded at a later time. This just shows an example of that zone architecture on a shop floor, and you can see towards the left-hand side there the letters MDC. It's a term we use for the micro data center, which is a telecom room, for example, on the shop floor. And then the use of pathways, common pathways to zone enclosures, which can then feed a variety of control panels. This is an example of how this hierarchy can be looked at here in this diagram. If you look towards the top part of this diagram, you can see home run kind of configurations leading from the telecom room to each of those nodes or control panels. This example shows how a fiber to the enclosure design could be used to fiber feed an enclosure and then have copper cabling links to each of some closely spaced control panels. This design is also available and applicable to topologies and configurations using resilient Ethernet protocol, which incorporates a ring design where you can see now that fiber cabling is used to connect each of these zone enclosures in a ring-like fashion. And the reason for doing that, of course, is because that gives you higher reliability. If, for example, a particular switch is fails at any point, then communication can still take place going through the reverse way around that ring. This is an example of a zone enclosure that's used for industrial applications. In a typical plant floor, these would be located, for example, on a pillar or in some kind of a support arrangement that's actually on the floor, especially installed for it. What you see here is on the top left-hand side of this image, you can see dielectric armored fiber distribution cable entering the enclosure. It then is taken through to the device that you can see on the right, on the left-hand side on the control panel wall, a slack spool, and then it's terminated and patch cords used to attach that to a DIN rail mounted distribution enclosure. The fiber is then fed itself to the through fiber patch cords is fed to the switch, and you can see the white cables are copper cables that are then taken out to a DIN rail patch solution on the right hand side, and then horizontal cables, copper, are taken out from that. So when do we want to think about using fiber? Some of the areas where we would want to use it is the switch-to-switch links in resilient Ethernet protocol. We've already mentioned this, and that allows us to get very high availability. Uplinks, of course, that go along those pathways that require higher bandwidth capabilities, and of course, especially extended lengths. Requiring low convergence time. We talked about the switch in the event of a failure. The ring will need to allow the communication to go in the other direction and effectively pick up where it left off. Takes a little time to do that, but with optical fiber, that tends to be just slightly bit better than copper cabling. Security, installations and applications. Environments that are subject to high EMI and noise, and of course it satisfies level 2 requirements with no spark generation. This is quite a complex diagram, but what it shows is how fiber can be deployed at all the levels of an industrial network. You may recall the slide quite early on in the presentation that talked about the what the typical shop floor looks like. We can see here on the left-hand side the micro data center is then fed by cable from a DMZ or an enterprise. Cabling, armored cabling then goes to that zone enclosure. We can use dielectric conduited fiber in those areas where we don't have adequate protection provided for the optical fiber. And finally, right at the end, at the node, for example, field installed optical fiber, so-called polymer clad fiber or PCF fiber, can be used in situations and really it's helped out by the installation. It's not as difficult to install as, for example, multi-mode or single-mode cable. So it's electrician friendly and provides very good installation reliability. So selecting the right fiber requires several things. First of all, obviously you need to know the equipment and the kind of network that you're connecting to. You need to understand the distance, what type of fiber can be used for that distance. You need to know the requirements for bandwidth, the fiber count, and then finally the type of fiber. And also, and peculiar or particular to the industrial environment, you need to know the kind of environment into which that fiber is going to be installed. Is it subject to mechanical forces or shock or vibration? What about ingress requirements of water and dust and other particles? So as you look at the first of those bullets, we talk about knowing the equipment that you're discussing. Here I'm actually showing a Rockwell Automation Stratix type switch, and on the left-hand side at the bottom left you'll see 4 ports. 2 of those ports are for fiber uplinks, and how that is done is using what we call an SFP module, small form factor pluggable module that attaches into that switch, into those fiber optic ports, and fiber is attached to the rear of the SFP module that goes into that. Let's just look at that in a bit more detail. The SFP modules will go into those 2 ports. There are 2 ports there. It really depends how you use it, but if you use it in a hierarchical star arrangement, one of those ports would be a main port, and then the other would be a redundant port. If you used the switch in resilient Ethernet protocol, for example, then effectively one of those ports would be used for the going round the ring clockwise, the other one would be for going round the ring anti-clockwise, for example. That's an example of what the SFP module looks like. And then you can see here on the rear end of the modular transceiver, this shows the very commonplace now so-called LC connector interface. On the right-hand side, you can see this dual connector type here, LC. The 2 ports are spaced about 6 millimeters apart, and there are many other fiber connectors available, but these are most commonly used in this kind of environment. The SFP module is also, it depends on the data rate that's used for the network, and that has an impact on the type of SFP transceiver that you require here. In addition, and we'll talk about this in a moment, you need a different type of SFP module depending on whether you're going to be using multi-mode fiber or single-mode fiber. And we'll talk a little bit more about that in a second. So now that we understand the equipment, we've got to take a look at some of the other criterion. We've talked about the type of cable and the bandwidth, the fiber count, the jacket rating, the application, kind of environment, the types of connectors being used, and then finally the loss budgets. The loss budgets permitted in the different optical fibers comes actually out of the TIA 568 document that we talked before, and they're just replicated here. So OM1, this is a multimode fiber type 1, and then multimode will have a maximum channel attenuation of 2.6 dB. OM2 has a channel attenuation of 3.6 dB, and you can see the rest of the values on the table. That channel attenuation directly influences the overall length that that optical fiber can support transmission. And you can see the types of distances replicated in this table. The fiber optic budget really is a way of describing the signal that is lost on transmission through the whole of that optical channel. There is a number of reasons why the attenuation occurs. There is a insertion loss or attenuation that takes place at each connection in an optical fiber channel. And in addition, there is a loss of signal per unit length along that fiber. On the top right, you can see some representative values here of, it depends on the wavelength at which the optical transmission takes place. For example, 3.5 decibels per kilometer at 850 nanometer wavelength. The term dB per kilometer is a measure of how much signal is lost over a length of a kilometer of the fiber. The dB is a logarithmic scale that basically, each time the power is halved, it reduces by 3 dB. So if you get to a point where you've lost half of the power, you have a 3 dB insertion loss. If you get to a further point where you've actually lost 3/4 of the power, so that you've only got 1/4 left, then you have a loss of 6 dB. And so you can see in the lower diagram here the combination of the loss per kilometer or loss per distance and the loss associated with each connector, or could be splice as well. And obviously the objective is to have a positive margin, that is, the received power is greater than the received sensitivity. This is a bit of a complex diagram, but I just put it in there for reference because it sort of shows the different attenuations of fiber, and basically, with an assumed connector loss for the OM2 type fiber, you can support. I'm sorry, for the OM1 type of fiber, you can support a 275 meter channel length. With the OM2 fiber, this is supporting 1000 base XX, which is a gigabit signaling. You can support a longer distance, 550 meters. So let's just talk about fiber itself. What sort of makes up the fiber? As I talked before, there are two basic types, single mode and multimode, that we'll sort of describe in this presentation. Single mode is used for longer distances, but it uses more expensive transceiver technologies. Multimode is suitable for shorter distances, and it's more cost effective for use in typical industrial environments. At the heart of the optical fiber, of course, is the core and the cladding. Both of these are generally made out of silica, and the cladding is just a slightly lower refractive index than the core. There's a buffer coating that provides protection to the core and cladding. That's surrounded by a strengthening material, aramid, which some of us may know as Kevlar, and then finally a durable, typically PVC or polyethylene jacket surrounds all of that. Single mode fiber, just the core and cladding. This shows you the kind of dimensions that the optical fiber is. 125 microns across, and the core is only 9 microns. The two types of multi-mode fiber, on the left-hand side, the OM1 fiber incorporates a 62.5 micrometer core, whereas OM2 through 4 occupy a 50 micrometer or micron core. There's also another type of fiber that we've mentioned, polymer coated fiber, where in fact the outside dimension of that is significantly larger and will allow you a much easier time of installation. So it's very useful to use in those kind of areas that require field installation right down, in the area of the control panel and the machine. And this complex diagram just shows all of these three together. So we've mentioned the term OM, optical fiber multimode. OM1, really this fiber is being used on legacy systems. There's a lot of it about in the field. Typically in a new installation, we'd recommend OM2 or OM3 to be consistent and future-proof. But there is a lot of legacy OM1 in systems. OM3 and OM4 are optimized fibers to enable longer distances. And we talked about OS, optical fiber single mode. There are two main types here, OS1 and 2. Both incorporate a 9 micron core, but the OS1 tends to be used with 1310 nanometer wavelengths, and OS2 with 1550 nanometers. And OS2 is also used more to describe optical fiber that's used in the outdoors or outside plant. So we've talked about optical fibers. We want to see some of the applications in which fiber is used. Outdoor or between buildings, long distances, EMI. Generally speaking, we would say the single mode is more expensive when used with the transceivers than a multi-mode equivalent. So that will give the cost of that will give us guidance. So there's a choice that can be made to use either single mode or multi-mode fiber. So the performance aside, it's really based on the cost factor of this. This is an example here which is showing a comparison between the use of multi-mode and single mode fiber. On the left-hand column you can see some representative prices of fiber per meter. For a certain length we can work out the fiber cost, and these are typical transceiver costs that you would see, and you can see the difference between the single mode and multi-mode transceiver costs. Given that this particular example was using 6 of these transceivers, you can see that this single mode configuration is costing more than twice that of the multi-mode. That's in those cases when you would need to consider the cost equations when you could use both fiber types. Obviously, if you had a 5-kilometer run to cover, then that would have to be covered by single mode. Multi-mode fiber would not be used in that case. So, in a way, the cost is not so much the issue. Here's another example looking at some different fiber types. This is armored fiber here, which is certainly more expensive than the previous example, and again shows here that the single mode is still more expensive, but obviously the difference now that the fiber is costing more is lessened. This diagram here shows fiber in the different ways that it is available. And I'll just talk about the left-hand part of this. You can see on the top horizontal run is showing an example where the armored fiber is used and is supported by J-hooks, for example. Very often these runs are made sort of across the ceiling, supported. The pathway itself is it's comprised of J-hooks spaced at regular intervals. The center diagram shows an example where a wire grid type pathway is used to support the fiber, and there we can use either the armored fiber or we can use, for example, dielectric conduited fiber. That is optical fiber surrounded by a very durable and hard-wearing and crush-resistant dielectric outer sleeve, effectively, and that provides a good protection against environments. And then finally, more conventional, less protected cable that would actually be typically run in a covered pathway. Looking at these in a little bit more detail here, one of the differences, of course, between the metallic armored cabling and the dielectric armored cabling that we're showing here is that the metal armoring would require consideration of grounding at both ends. So what would happen is the armored cable would enter into, for example, a metallic enclosure, and attention would be paid to properly bonding that outer armoring to the ground potential point of the enclosure, and that has to take place at both ends. So that just gives an example of what does a metallic armored cable look like. Very often, very much state of the art. These are available with a variety of fiber counts. You can see through here all the way up to 144. These are often available in all of the different modes, both multi-mode and single-mode fiber types we'd identified. This just shows some examples of how that optical fiber could be deployed in a typical sort of shop floor environment. You can see on the top left there, the optical fiber is actually leading into a type of zone enclosure, and the bottom right-hand side with cleats and clips attached to the walls. The dielectric armored cable we've talked about. It has also a benefit that it's significantly lighter than the metallic armored cable. It has a better bend radius, and we've already mentioned that it can be deployed without being installed into conduit or some kind of covered pathway. So it can be used with J-hooks and a relatively undefined pathway. Typical application for the fiber that we've seen near the shop floor is a device level ring, for example, that's used again to promote resilient Ethernet networks. Also want to mention the other type of fiber we talked about. That's PCF, polymer clad fiber. The diameter of the cladding, of course, is significantly larger. It's now 200 microns, and rather than the 50 that we saw before. And what will happen is that really aids and helps the installation of the optical fiber. Typically, it's used at lower data rates, 10-100. And typically, we've seen it used for OM1 legacy installations and OM2. You can get these in so-called breakout cables, 2 or 4 fiber. They're also supplied in a duplex zip cord that you can see on the bottom right hand side there. Connectors have been developed for polymer clad fiber cable, again focusing on the LC connector, and this can be used for like a direct attach field installed build. The current termination technologies, you can can be handled by operators who have received little training in this. Highly reliable to get a fully secure and high performance connection. And that just shows some of the easy steps with the tools. So it's basically install the connector into the crimp itself, prepare the cable, insert that into the crimp, the connector already loaded, crimp it, cleave it, cut the fiber, and then install the back shell. So what about cable in the real world? We've talked about the difference between the industrial and the enterprise environment, and so what happens here is that we need to be aware of the environment, and we refer to a term used in the TIA 1005 as MICE. MICE stands for mechanical, ingress, climatic/chemical, and then electromagnetic. And basically a level 1 is typically an office environment. As you move through level 2 to level 3, that might be found in industrial. And this sort of talks about the environment, and that consideration of the environment gives you a reflection of what has to happen for the performance requirements of your fiber. So some of the other fiber types that we see here are the so-called indoor fiber that might be used in the enterprise or going from the enterprise to the micro data center, and then the use of armored clad fiber as you get more onto the shop floor, and dielectric armored fiber and polymer clad fiber. Having installed the optical fiber, now comes the point of actually testing it. There are test sets to allow you to test that installed permanent link. It validates the performance against the standards and requirements outlined and given in TIA 568. It will allow you to identify connections with a high loss, for example, if the termination had been made poorly. And it finds connectors with a high reflectance or reflectivity levels. So leading towards the conclusion here, a summary of some of the factors that influence the fiber type. Obviously the connectivity count, or how many fibers would you include in that armored or that distribution cable. Obviously that depends on the number of devices and the number of machines. The environment itself, what level of protection has to be provided by that fiber? Is there anything else in the vicinity, for example, copper cabling or power cabling? The bandwidth, which depends on the current network utilization, but must emphasize also to look into the future and future-proof that fiber. The cable reach, obviously, anything over 100 meters is going to certainly give the most serious consideration to fiber. And then finally, safety, security, and longevity. So summing this up, we can kind of, as we step through this presentation, we can look at the best practices that have really sort of been outlined here. The starting point, I always think, is the adoption and the use of the converged plant-wide Ethernet topology. Focus the designs on standards. I talked about the TIA, of course, but in other parts of the world, IEC and ISO standards, for example, 11801, is very aligned to TIA 568. We talked about the zone topology as a way of consolidating a high data rate cabling up defined pathways or along defined pathways. We identified the targets for optical fiber, and then finally understood how to select the right fiber. Know the equipment and the network you're connecting to, understand the distance requirements and the fiber count, and then finally make consideration of where or what type of environment this fiber is going to be installed into. And then finally, measure the permanent link performance. So just a couple of slides here that will give some additional references. Design guide for fiber and industrial applications that you can see here, and then a copy of the Converged Plant-Wide Ethernet design and implementation guide. Some of the other resources, talking about the integrated network zone system that sort of promotes and outlines zone topology, information on the Stratix Rockwell automation type switching, talk about zone architecture video, and then various design tools that can be found in software. So with that, I'm now going to hand it back to Mark, and would like to thank you once again for your attention today.
Thanks very much, Bob. That was a terrific presentation. Now we'll get to a few audience questions. The audience listening live can type questions for today's presenter in the Ask a Question box on the screen. We will get to as many questions as we can, and then within a few days the presentation will be available for on-demand viewing. We'll post the archive on the Control Engineering website and then send out an email message with a link connecting directly to it and to related resources after it's ready. Now on to the questions. I will move back to the resource slide during the Q&A, but do please continue to submit your questions. First question, Bob, what cabling issues are you seeing at the 100 megabit per second Ethernet over fiber copper?
That's a great question, and it's good in a one way because it recognizes one of the things that we're seeing in the industrial application is increasing data rates. Industrial networks down at the control panel and at the machine, data rates tended to have been slower at 10 megabits per second, but we've seen that these have increased up to making many uses of 100 megabits per second. Some of the things that happened on optical fiber, copper cabling, for example, would be the need to really understand the shielding that is associated with, for example, shielded copper cabling. The idea of proper bonding practices of the shield to the enclosures at both ends, consideration of ground loops that might occur if the utility feeds different parts of that industrial application. On the fiber side, really what we've seen is a transition from legacy OM1 through to OM2, but these fibers have very reliable performance in supporting 100 megabits per second, and in fact they're very well future-proofed to support certainly OM2 through to gigabit, and with the optimized fibers OM3 and OM4 are even suited to support 10 gigabits per second should that ever be required. Of course, the transceiver would need to be changed associated with that increase in data rate.
Good, thank you. Can you go over the difference between OS1 and OS2 single mode fiber? You talked about a lot of different kinds. Maybe you could review the differences there.
Right, there are two main differences. OS2 is the specification for OS2 allows it to be used in an outdoor environment. The issue with using fiber outdoors is that it's subject to much more temperature variation in an outdoor environment than in, for example, a more benign enterprise type of application. And if you recall one of the slides that talked about the construction of the optical fiber, I mentioned that the buffer was a protective coating that was actually put around the cladding, the actual silica itself. And that, there can be sort of micro cracking that can occur due to differential expansion in those larger varying temperature kind of situations. So OS2 is made of a different construction, and it actually incorporates a loose tube that is placed around the silica that's there more for protection. So it allows that differential movement.
Good, thanks. One of the benefits of twisted pair copper cabling is that it can support power. Any comments about how fiber can support power as well?
Yeah, that's a great question, because the idea of twisted pair copper cabling is of course, as folk will know, it's capable of supporting power over Ethernet, so-called PoE, and those standards are changing and developing. First standard allows you to support about 13 watts at the far end. That's been increased now through standards-based work to 25 watts, and even higher powers are being looked at as well. What we've tended to find is there is a call for optical fiber to support power in specialist applications like video surveillance. For example, you have a surveillance camera at the far end of a large industrial campus, for example, and they are at that because they will be at corners and areas to provide that coverage. And what happens is it's longer than 100 meters, so PoE in that sense can't be used. What we have seen is we've actually seen a hybrid cable being used where optical fiber would support the data, and there'd be a larger gauge conductors that also run in the same jacket as that optical fiber to supply the power. In actual fact, more in the industrial environment, we haven't really seen this to be too much of an issue, and the reason is because the switch will take more power than is just available by PoE on its own, and certainly if you have additional equipment in that enclosure, so that it's usually utility fed at that point, at the point of an enclosure anyway. So it tends to be just a data, an optical fiber data cable that is run between those enclosures in one of those figures that I showed, the resilient Ethernet protocol.
Sure. What influences the number of cores for fiber optic cables?
It really depends on how the idea of the number of cores. It's going to be influenced by the number of devices you connect to, but also the way that you connect those devices. We've talked about resilient Ethernet protocol. Really, since we're attaching one switch to the next in a ring-like fashion, in actual fact, you literally would only need the 2 cores for each one of the SFP modules that we used in the switch. Whereas if you used, for example, a bus type of topology, what happens is you would use, say, like a distribution cable with a number of fibers within the jacket, and literally you would drop off however many you need for each device. It might be 4 fibers, one for 2 for the main SFP module, and then another 2 for the redundant SFP module, so that you would drop 4 off that distribution cable, and the rest of the cable would go on to the next device, sort of further down in the network.
Very good. Well, what type of fiber solution is recommended for 100 gigabit per second speeds? Would that be OM4 or higher? And then for longer distances, would it be OS1 or OS2 or something beyond that?
You mentioned that I think you said, did you say 100 gigabit or 100 megabit?
100 gigabit speeds.
Well, certainly you need OM4 for those type of data rates, but we're certainly not seeing those kind of data rates in an industrial environment. What we're seeing at the moment is certainly on the uplinks for the switches that are located on the shop floor, we're seeing single gigabit solutions, the uplinks from the switch, whereas the downlinks we're seeing at 10/100. So I don't think I've heard of any application so far that would require 100 gigabit. Where 100 gigabit would be required is in some extremely high performance data center application, and I know the standards organizations, the IEEE, for example, is looking at those type of standards, and there certainly have been transmissions that have taken place at those high data rates, but don't see anything for that kind of use at the moment in a typical industrial application.
Good. Is there a validation tool for fiber?
Well, yes, we mentioned that in the presentation the need to measure the performance of the permanent link. That is what would typically happen there is optical fiber would, let's say, connect 2 of the 2 switches that are located in zone enclosures. What would happen is the fiber is actually terminated, and then it's connected to an adapter that also takes a patch cord to attach the to the SFP module. At that fiber connector that's field installed, that whole permanent link, as it's called, can be tested using basically an OTDR, which is an optical time domain reflectometer, which measures how much power is reflected from various points of mismatch along that optical fiber. And what happens is that can be validated by a certified installer, and typically the results are retained and kept as part of the manufacturing IT group.
Great. Thanks very much, Bob. And thanks to the audience for the great questions. For the ones that we didn't get to, Bob has offered to answer those offline, and we'll post those with the related resources with the webcast. So I thank Bob Elliott, Business Development Manager, Industrial Automation Infrastructure Group for Panduit, for sharing his expertise today in the presentation and the Q&A session. I'd also like to extend special thanks to our sponsor, Panduit, for sponsoring today's event. And now that we're just about done, we want to hear how we did. The exit survey will pop up on your screen just as soon as the webcast ends. Please take a moment to complete it as we use the information to improve future webcasts. On behalf of CFE Media and Control Engineering, thanks for attending the webcast. Copyright 2015 CFE Media. This concludes our webcast today. Thank you very much.